This conference will now be recorded.
Okay, so last time we studied Newton's method and secant method in the videos, right? So I think I stopped here. This was the secant method. Okay, so I will do another example here, which we did for the Newton method as well. This one, we did this for the Newton's method. X is equal to cos x, right? Just above. This was the secant method. Okay, so for the secant method, we can do this example as well. So if you go back and see the formula for secant method, this is the formula for secant method 2.12. Pn is equal to Pn minus 1. So here I told you that we need two initial guesses, P0 and P1, to get P2. So what's wrong? So let me use that. So if we replace fx is equal to cosine x, because my function is now cosine x minus x. So here, let me start from here. So our fx here is fx is my cosine x minus x. Okay, you can take it as x minus cos x as well, because our equation is cosine x is equal to x, right? This is our function. So basically, either you can write this as cos x minus x equal to 0, or x minus cos x equal to 0. Both are fine. So you can either take this as your function or this as your function. Okay, both are the same. In this book, they wrote it cos x minus x, so that's why I'm writing like that. Now, if you go back, what was our formula? Our formula was Pn minus 1 minus Pn minus 2. This was our formula. And then here I had f at Pn minus 1. This was, so this is cos Pn minus 1 minus Pn minus 1, because my fx is cos x minus x. So I replaced from here. So if you want to find what is fPn, it means it is cosine Pn minus Pn. Okay, so basically cos Pn, you will solve this separately, then you will subtract Pn. So here I got this one. Downwards again, we have the same thing, fp minus fpn minus 2. So our formula was fpn minus 1 minus fpn minus 2. Okay, so this is the value of fpn minus 1, this is fpn minus 1, and this is fpn minus 2. This is fpn minus 1. So these are the three things which will be replaced, because I have to replace my function. This function will be replaced, fpn minus 1. These are the formula. So I just replaced, so this is my new formula. Now how we are getting the iterations, right? Because I needed two of them, it starts from n greater than equal to 2. So if I take n is equal to 2, I will get p2 on the left. You see, n is 2, so p2 on the left. On the right, I will get p1, because n minus 1 is 1, and minus p1 minus p0 cosine p1 minus p1 divided by cosine p1 minus p1. This is f at p1 minus f at p0. Okay, so I got for n is equal to 2. You see, if I replace n is equal to 2, I got 0 0 here, 0 0 here, and 1 1 here, 1 1 here. So this is what I got. Now because my p0 is 0.5 and P1 is 0.75. We took 0 and pi by 4 as our initial two guesses, 0 and pi by 4. So I will get the next one. P2 will be, P1 is pi by 4, which is calculated in radians. It's not 45 degrees. Pi is 3.1416. So if you divide 3.1416 by 4, you will get this 0.7853. This is pi by 4. Minus pi by 4 minus P0, which is 0.5. Cosine pi by 4 minus pi by 4, because it is at 1, divided by the same thing, cosine pi by 4 minus pi by 4, minus cosine P0, which is 0.5 minus 0.5. So if you calculate these things from the calculator, you should get this P2. This is your new P2, which is coming from here. Okay, so this is what you will get, 0.73, 0.7363841388. You can try right now. You can try right now whether you are getting this or not. Use pi by 4 is not 45 again. Pi by 4, use pi in the calculator. There is a pi in your calculator. You divide by 4, you will get 0.7853. Similarly, now if you want to do another iteration, P3, let's say if you want to do P3, this is P3, how they got it? P3 will use, I will use n is equal to 3 for that, right? So P3 will be P2 minus P1 cos P2 minus P2 divided by cos P2 minus P2 into, minus cos P1 minus P1. 0 will become 1 and 1 will become 2. You see, 0 will become 1 here, 1 will become 2. So on the left side, you will get 3. Okay, so now P1 and P2. So you will not use 0 now. I don't need this now. I need P1 and P2 to get P3. Okay, so if you use this is P2 minus P1. If you use P2 and P1 from here, these two values, if you use these two values in this formula, you should get your P3, this one. So again, from calculator, you can see whether you are getting this or not. 0.73905. Okay, so just check it. So same way you will continue your iterations. So P4 and P5, you see, up to 6 decimal places here, your answer is the same. You see, P4 is 0.7390851 and P5 is also 0.7390851. So up to 7 decimal places almost, you see, 7, 1, 2, 3, 4, 5, 6, 7, up to 7 decimal places, your result is the same. So it means you can stop here. No need to find P6 because P4 and P5 almost repeated itself. So whenever your iteration starts repeating, that is our answer. We will stop. Okay, so you can complete, of course, these two. So if you are able to do one iteration, of course you can do many iterations. So this was something which we studied in the previous one. I stopped, I just gave you the formula last time and I thought you will be able to do it. Now if you recall, your secant method was what? This was the secant method, right? I did this picture before as well in the last lecture. What we do basically, we take P0 and P1, any two gases, P0 and P1 on the graph. These are the 2 points. So we draw a secant line. Secant line is any line that passes through 2 points of the curve, right? This is a secant line. So secant line hits this point P2. So what we got from here, the second iteration that we got from here, P2, is basically this point where the secant line passes through P0 and P1 touches the x-axis. This is my new point. Now we will ignore this one and I take P1 and P2. Now P2 P2 is this point and P1 is my old point. So I will again draw a secant line from P1 and P2 to get this P3. Okay, now I will draw P1 and take P2 and P3. Right? We take the previous. So P2, P3 are these 2 points. And if I draw the secant line, so I have to extend it to get to this one. This is my P4. Now I will ignore this. I will drop this and take P3 and P4. P3 and P4. So from P3 and P4, P4 is here, right? Point P4 is here. This is P3. Again, draw a secant line. So your P5 is almost at the root. So this is what you are getting. This is the secant method. Okay. There is another method which we call method of false position. Another method which is called method of false position. This is similar to secant method, but the book also says that we do not recommend this method much. Why? Because it's very similar to the secant method. But we should know what is method of false position. The other name is regula falsi. Regula falsi method or method of false position. It's the same thing. You see, at this step, if I go back and consider this step here, P2 and P3. When I reached to this step, P2 and P3, we got off to from P0 and P1, and I got 2 new points. Now both points P2 are below the x-axis. You see, both are below the x-axis. So f at P1 is negative. F at P2 is also P2 and P3 are both negative, but we don't care. It's not a bisection method where we check the signs of P2 and P3, right? So both are negative, no problem. We can still take the secant line and extend it to x-axis and get this P4. So secant method does not ask you to check the signs of your function at these 2 points. In regula falsi method or method of false position, what we do at every step, we update the points. We need 2 points at every step, but we do not consider the newest two. In secant method, when I have P0 and P1, from there I get P2. So I will drop the very first and consider these two. Then from here I get P3, so I will drop the oldest one, P1. I got P2, P3. From here I get P4, so I will drop P2 and get P3, P4, no matter what is the sign of the function at these points. In method of false position, what we do, we keep one positive and one negative, like in bisection method. So this is also bracketing. We call it bracketing, right? So what we do here is, you see, at P3 and P4, when it's the same example. So from P0 P1, I got to P0 P1 and P2. P1 P2 give me P3, and from P3 both are negative. P2 and P3 both are negative. So we do not drop this P2. What we do is we consider one from here. You see, from P1 and P2 I got P3. So P3 is negative because f of P3 is negative. So I do not consider P2 and P3. I drop this one and I go back to P1. Why? Because f at P1 is positive. So instead of taking the newest two numbers, we are not taking newest two. From P0 and P1, I got P2. Because P1 and P2 had opposite signs, you see, P1 is above, P2 is below. Because they have opposite sides, so I dropped P1. From there, I got P3. In secant method, I dropped P1. But here I'm not dropping P1, I'm dropping P2 and considering P1 and P3. What is the reason? Because P1 is positive and P3 is negative. Function value, sorry, not P1, P3. The function value at P1 is positive and the function value at P3 is negative. So at every step, if you decide which point, because at every step you have 3 points. From P1, P0, P1, you got P2. So you have 3 points. So I will drop one of the previous two. P0, from P0 and P1, I will drop one of them. So I will drop the one which has the same sign with the P3, because P2 had the same sign with P3. So I dropped P2 and I picked the point which had the opposite sign. Got the idea? So this is the only difference between secant method and method of false position. We use the same formula, both uses the same formula. Okay, both use same formula. Formula is not changed, only the updation of the points, the criteria of updation is changed. Okay, so we think that because both are negative, so see, you are going far away. So when you took P3 with P1, not with P2, then this is your new secant line. So every time your secant line will give you x-axis in the middle. Here the secant line did not have x-axis in the middle, so I had to extend it to the x-axis. I have to go out of these points to go to x-axis, and it can take you very far. Let's say if the point is very close here, your secant line may go like this, and it may take you very far from your point. Okay, but in practice we saw that method of fast position is not very fast method. It may not give you faster results. Okay, this is just another idea, but it may or may not give you fast convergence. So when something is not giving me fast convergence, okay, then it is not very helpful. May or may not be faster. Okay, than secant. So it may or may not be faster than secant method. So it means if you use it, it's okay. If you don't use it, it's still okay. I can show you an example in the book right after this. They gave us the example where they solved the same question, x minus cos x, by uh, by this method. You see here, same example, x minus cos x. Here it's the same example, f x. It is the same example which we are studying, cos x minus x. Same secant formula with p naught equal to 0.5 and p2 equal to p1 equal to pi by 4, which was 0.78 something. Okay, pi by 4. So you can find pi by 4 here. So here you see a Newton method was very faster. We did this example with Newton method as well. Only at P4 I got the accurate result. Here I needed one more iteration for the secant method. But here P6 gives me the same answer. So false position method took one more iteration to give you the same answer, which secant method gave you in just 5 steps. Okay, so this is the reason it may not be faster than secant method, but it's just another approach. Some people like updating or bracketing the roots. They like to be one of them to be positive and one of them to be negative. So it's the same example done by regular Falsi method, secant method, and Newton method. So just to give you the comparison, that they are not very, and it's not very slow as well. If this is giving me P5, it's not that I got 5-6 more iteration. Just one more iteration gave me the answer. But this is not a hard and fast rule. In some example, it may take many more iterations than secant or Newton. All right, so Newton method is still the best. You can see from this table. After that, sometimes you know that from your calculus or basic mathematics, maybe in the foundation or in the high schools, you remember sometimes your equations have multiplicity more than one. For example, if your fx is x minus 2 square, right, you know that f has 0 at 2. 0 at 2. What does that mean? That f of 2 is 0, right? F x is equal to x minus 2 also has 0 at 2. This function is 0 at 2. This function is also 0 at 2, right? But here there are two factors. Square means two factors. It means one is x minus 2, another factor is also x minus 2. So if I put this function equal to 0, I got 1, 2 from here and 1, 2 from here. So there the same root repeated twice, right? So we say that x is equal to 2 is a 0, or we say root as well, is a 0 a root of fx with multiplicity 2, with multiplicity 2. Got it? So this is simple root. So this has multiplicity 1 because this is the only root not repeated twice. So if some root repeats twice, it has multiplicity 2. Similarly, it can repeat any number of times. Let's say if the power is m, this is also called simple root. Okay, when multiplicity is 1, we call it simple root or simple 0. Okay, and when it has multiplicity 2, we call it double root or multiplicity 2. Similarly, if you have any factor, let's say x minus 2 or some root, let me not write 2. If your function is x minus some number a to the power m, and you can have any other function with it, another function with it, right, which is not 0 at a. Phi x, phi at a is not equal to 0. So only this part gives you 0. Phi does not give you 0. So here x is equal to a is a root with multiplicity m, right? Because the power is m here. There are m factors of x minus a. So this has multiplicity m. So we call them a root with multiplicity m. So what happens if you do not have a simple root? Then we have another method which is based on Newton's method. We call it modified Newton method. Okay, so suppose fx is continuous, right, on AB and has a double root or multiplicity 2 at x is equal to a, then your f at a is 0 and f prime at a is also 0. Whenever your root is double, your function will be 0, of course, because it is a root. So this has to be true all the time. This is an extra thing. Its first derivative also becomes 0. Okay, here you can see what is the derivative of this function. What is the derivative of this function? 2 into x minus 2, right? You see, this is still 0 at 2. If you put x equal to 0, 2 minus 2 is still 0. So first derivative is 0, but second derivative is not 0. If you take second derivative is just 2, which is not equal to 0. So only the first derivative will be 0, second will not be equal to 0. But here I should write, but second derivative at a is not equal to 0. Similarly, if you have a root of multiplicity 3, then all up to 2 will be 0 and the third derivative will not be 0. Okay, so if f is continuous on AB, what does this mean? F is continuous on AB can be written as this in short. It is the same thing. F belongs to a set of continuous functions from A to B. This CAB means it's a set of all continuous functions from AB. It means this fx is also one of them. So this is a member of. F belongs to, F is a member of continuous functions which are continuous on AB. If F is this and F has a root of multiplicity m at x is equal to a, if and only if, double F means if and only if, right? If and only if your function is 0 at a because it is a root, its derivative is 0 at a because it's a multiple root, and all derivatives, not just this, all derivative before m, so m minus 1 derivatives will be 0, right? But the mth derivative will not be equal to 0. Like here, when it has a root of multiplicity 2, the second derivative was not 0 and all other derivatives were 0. Okay, second derivative was not 0, all other derivatives were 0. So here, if you have a root of multiplicity m, then the mth derivative will not be 0, all derivatives before that will be 0. So this is the condition for any function to have root of multiplicity m. Okay, so for double root we can modify our Newton method like this. You see, if you recall, what was the Newton method? I can recall one more time. Newton's method was Newton's method or Newton's-Raphson method. They are the same methods. Sometimes they are called Newton's method only. So Newton-Raphson method says your Pn is Pn minus 1 minus f of Pn minus 1 divided by f prime Pn minus 1. Right? So let's say if f has a double root means multiplicity 2 at x is equal to p, right? P where it will converge, right? So because you start from p naught, this gives you p1, this gives you p2, this gives you p3, and so on. You continue. So if you have a solution, then with n goes to infinity, you will get exactly the root p, right? Exactly the root p. Now you see, if as you are approaching this number p, these both will approach 0, because if it is a root, then fp will approach 0. And because it's a double root, in the double root your first derivative also goes to 0. You see, in the double root your first derivative also goes to 0, so this also goes to 0. So as n approaches to infinity, this portion becomes 0 by 0 form, right? 0 by 0 form. And you remember from calculus, this is called indeterminate form. Indeterminate form may or may not have a solution. Sometimes it gives you a solution, okay, but sometimes it is not defined as well. So we may have a problem. Even though this may have a solution, the convergence of Newton method slows down. This Newton method will become slower. If it has a double root, you can still apply Newton's method, no problem. But it may give you a slow convergence, means it may take more iterations. When we say that the convergence is slow, it means it will take more iterations to give you the solution. So instead of that, uh, someone suggested that take this function, let me write this as a function, fx over f prime x. Define this function as a new function, let's call it mu of x. Okay, and apply Newton method to mu of x, and apply Newton's method on mu of x. What does it mean? It means instead of using f here, use mu. If we use mu instead of x, then this will be here. If you use mu here instead of f, then it is called modified Newton's method. And this will give you faster convergence. Both are applicable. You can apply any one, but this will take less iterations to give you answer. Of course, in numerical methods, you say if we are not interested in faster convergence, this is what we call efficiency. If we are not interested in the efficiency, then only the first method, which is bisection method, was enough for us, which we studied very first method, bisection method was enough. In numerical analysis, people are still researching on numerical methods of equations. Why? Because we want efficient methods, we want faster methods. Okay, that's the reason we are getting more and more methods here. So modified method becomes I will not. You remember we write x is equal to x minus mu x over mu prime x. This is what I said. Instead of using a method on f, use it on mu. Okay. Now you remember mu is f over f prime. So I need the derivative. So what will be the derivative here? I will use the quotient rule. F prime square f prime uh, f prime minus f f double prime. Right? This is the quotient rule. So if I replace that, I will get here. I will get x minus mu x. Mu x is uh, f over f prime. This is mu x divided by mu prime, which comes from here. Okay, I replace this mu here, and I will replace this here in the denominator. So f prime means f prime square minus f double prime and divided by f prime square. So one f prime is cancelled with this square. Okay, and then the remaining f prime will come here. So I got x minus f from here, and this f prime comes up with f prime with f. So f prime divided by f prime square minus f double prime. So this is the modified Newton's method. So if I want to write in terms of p, not p1, p2, you remember that we replace pn minus 1 here. We replace pn minus 1 here and pn here. Why? Because the previous point gives you the new point. So modified Newton's method becomes pn equal to pn minus 1 minus f at pn minus 1, f prime at pn minus 1, right? F prime divided by f prime square. So again, it is f at pn minus 1 square minus f and f double prime. So f at pn minus 1, f double prime at pn minus 1. So this is my modified Newton's method. So whenever you have a root with multiplicity 2 or root with double root, you can uh, use this method, which is called modified Newton's method. Okay. So this is the extension, you can say, of Newton's method. So this gives you the faster convergence. Both will give you the answer. I'm not saying that the Newton method will not give you the answer. Where is the Newton method here? This one. Newton method will give you the answer. Okay, here this one. This will give you the answer. Only the convergence will be slowed down. So to make it faster again, you can use this one. This may be a little hectic because too many functions are going on here, f prime and f double prime. So it may cause you trouble. Okay, trouble in just calculating. It's not that it will not give you a solution. So if you find couple of exercises on your own, it will be easy. Let me check where this was. This one, modified Newton's method. They used it here. Okay, this is the example. This is the example in the book on page 84. Okay, so on page 84 in the book, I will paste it. I will paste this here in my OneNote file, and I will upload um, these notes on Moodle as well. Okay. So right now I'm telling you from here. So see, this is the modified method. P naught minus f p naught f prime p naught divided by f prime square. This is not just p naught square. This is the square of this whole thing. Okay, square of f prime minus f p naught f double prime p naught. So here they found the values at different points and got the solution. This is just one iteration which they showed, but here this is from the modified method. And this example was also done with Newton method as well, because you see how they said it has a zero of multiplicity 2, zero of multiplicity 2. How they have a zero of multiplicity 2? Let me show you here. Ex minus x minus 1. Example 2 on page 84. Fx is ex minus x minus 1. So f has zero of multiplicity 2, or you can say it is uh, at x is equal to 0, or you can say that it has double root. You see, f at 0 is 0, e to the power 0 is 1, minus 0 minus 1, so it is 1 minus 1 0. But if you find the derivative here, f prime is ex minus 1 minus 0, right? The derivative of x is 1. Now put 0 here, f prime at 0. F prime 0 is e0 minus 1, which is 1 minus 1 again 0. So you see, multiplicity 2, it means function and its derivative are 0, but the second derivative should not be 0. Otherwise, it will have multiplicity 3. So if I take second derivative, it is just ex minus 0. Now you see it is not 0. F double prime at 0 is 1. E to the power 0 is 1. It's not equal. So you can easily prove that f has a multiplicity 2. Multiplicity 2 means f at 0 should be 0, f prime at 0 should be 0, but f double prime at 0 should not be equal to 0. Right? These all things should be true. So it has a multiplicity 2. Now we can easily use the method. My modified Newton's method give you modified Newton's method gives Pn Pn minus 1 minus f at Pn minus 1, f prime at Pn minus 1, f prime at Pn minus 1 square minus f at Pn minus 1 and f double prime. F with f double prime and f prime square. So this is what you have, right? So if this is for n greater than equal to 1. So if I take p naught is equal to 1, I think they took p naught equal to 1. Let me check. Yeah, they started with p naught equal to 1. Yes, here. P naught equal to 1. So if I take p0 equal to 1, I can get. So let me put the values first. Pn is equal to Pn minus 1 minus function at Pn minus 1. Or let me use, it's easy if I write number first. For n is equal to 1, I will get p1 p0 minus f p0 f prime p0 divided by f prime p0 square minus f p0 f double prime, right? You can find all these values. P0 is 1. With p0 1, what is f of p0 means f of 1. F of 1 is e to the power 1 minus 1 minus 1. So e minus 2, right? Similarly, f prime at p0 is f prime at 1. F prime at 1 is e to the power ex minus 1 was the derivative. So e1 minus 1. So e minus 1 is this. And f double prime at p0 is f double prime at 1. F double prime at 1 is just e to the power 1, which is 1. I have all these three derivatives above. So I am putting here. F of 1 is e to the power 1 minus 1 minus 1. So it becomes e minus 2. Here f prime at 1 is e to the power 1 minus 1. So e minus 1. F double prime at 1 is e to the power 1, which is e. So now I can put all these values here. So P naught is 1 minus F P naught is E minus 2. F prime P naught is E minus 1 divided by F prime is E minus 1 square minus FP is E minus 2 and F double prime is E. Okay, so this is what you can calculate easily by using calculator, and you should get this root. There is also a button E in your calculator. If you see, there will be a button ln, and below it it's written ex. This is ex, right? So if you press this ex and then press 1, if you press, I think with shift, you have to press this button with shift. When you press shift log, it gives you E, and then you put 1 and hit enter. So it gives you the value of E. E is 2.71828, so on. But don't put this value, don't put 2.71828. Get E from the calculator. E will take the accurate value calculator. So if you use this one, it is the same thing which I wrote over there. You see, 1 minus E minus 2, E minus 1, E minus 1 square, E minus 2E. So that is minus 2.34, 10 to the power minus 1. 10 to the power minus 1 means it is minus 0.2342. Okay, so this is what you should get, minus 0.234. Okay, so you can verify. So similarly, you can get more steps. After getting this P1, you can find P2. P2 will be P1 minus f of P1 f prime P1 divided by f prime P1 square minus fp1 into f double prime P1. Now put this P1 here. Calculate all these three values at f of P1, this point here. Okay, and calculate f prime, f double prime. Calculate all these three things, put them here, f prime, f double prime, put them here and get the solution, and this should be equal to your next point, which is this. Okay, this is P1 and this is P2. So just check, at least try one iteration. If you, after P1, if you can get this number P3 correctly, P2 correctly, it means you know how to use this formula. That will be enough. But for your practice, you can do more iterations. Of course, the more you do, the better you will get at these things. All right. So let's stop here. It's too much for me. I will post some questions. Try those questions, and after trying those questions, we can have another help session to solve your difficulties.